All right, so before we get into logs, I'm going to show you how to solve some exponential equations without logs. There are certain types that we can do that with. If we had 3 to the x equals 8, that would be a problem because 3 to the first is 3, 3 to the second is 9. So it would be 1 point something. But it's hard to get a precise answer. But with this particular one, I can just kind of do this mentally. 2 to the first is 2, 2 to the second is 4, 2 to the third is 8. So only 3 would work as x, right? So you can kind of just think through it sometimes if you've got a simple enough equation, and then there's no need for logarithms, okay? On this next example, hey, I've got variables in the exponents again, another exponential equation. But here on both sides of the equal sign, I have the same base. So I can think of it like this. 3 to the x minus 7 equals 3 to the 2x minus 2. Hey, 3 to the something equals 3 to the something else. That means the something and the something else have to be equal. So that means the two exponents are equal. So I can just set them equal to each other to figure out what x value will work here, right, to make those two exponents equal. Okay, and then I got a pretty simple equation to solve. I'll just subtract x. And add 2, and then x will equal -5, and there's my solution. And you could try it, you can test it out in the original equation. It will balance out on both sides. Okay. So on this next example, I don't have the same base, but I can rewrite this with the same base. So 2 is the smaller of my bases. So usually what I start with is I think, well, can I write 8 as 2 raised to some power? And I can, right? Because 2 to the third is 8. So I'm going to leave the left side as is right now. But the right side, I'm going to rewrite it like this. Okay? And now I've got the same base, so I can set the exponents equal to each other. Before I do that, I want to simplify this exponent a little bit over here. Okay? So again, I'm going to leave 2 to the 4x alone. Remember, when you're raising an exponent to another exponent, what you're going to do is multiply the two exponents together. And don't forget, a lot of people will just write that 3x plus 4 without the parentheses, but you're tripling the quantity x plus 4, right? So I'm going to have to distribute that 3 over there. So that's the biggest mistake, is people just forget to distribute on problems like this, or the most common mistake, I should say. Okay? And now I've got the same base, so I can say, okay, these two things have to be equivalent for this equation to balance out. So 4x must equal 3x plus 12, and I can solve that just by subtracting 3x from both sides, and x is going to equal 12. Okay? Yeah, so I rewrote the 8 as 2 to the third and proceeded from there. Okay? So the next example at the top of the page here. Now these don't have the same base, so I'd start by thinking, okay, can I write 8 as 4 to the something? But 4 to the first is 4, and 4 to the second is 16. So it's not going to work with a base of 4. So if you can't use the smaller base as a base, think maybe sometimes there's a base that's even smaller than that that's going to work out. So I'm thinking, okay, something less than 4 that could be a base for both of these. Well, 2 to the second is 4, and 2 to the third is 8. Okay, of course this isn't always going to work. It's only going to work when it just so happens that you can write, sorry about the bell there. I wrote that as 2 to the third. I meant 2 to the second. This method is only going to work when it's just kind of set up so that you can write both sides with the same base, which I can here, okay? And then when I simplify the left side of this, 2 to the 4x, when I simplify the right, I'm multiplying 3 times this binomial, right? So don't forget to distribute that. So it's 2 to the 3x plus 3, not 3x plus 1, okay? Now I set the exponents equal because I have the bases equivalent. And subtract 3x from both sides. And x equals 3. Okay. All right. This is another instance. This one looks a little complicated. I can't write both sides with the same base. Well, actually, I can write, I take that back, I can write both sides of the same base. It's a little weird though, but remember anything to the 0th power equals 1. So when one of the sides of the equation equals 1, you can write it as with any base to the 0th power. And now I'm in business, right? So now 2x plus 10 is going to equal 0. So that means 2x equals negative 10 and x equals negative 5. And you can always test out these answers, right? Go back to the original equation and plug your x value in and see if it works. Okay. Here's another one that is a little trickier. When you've got 1 over something, that means you can write this as something with a negative exponent, okay? So I'm thinking, okay, base 3 would be great to use, and I know 3 to the 3rd is 27. Okay, now it's not quite ready because I still got 1 over 3 to the 3rd, but hang on, 1 over 3 to the 3rd would be the same as 3 to the negative 3rd, right? If I simplified 3 to the negative 3rd, it would look like that, right? Okay, and now I've got the same base, so x is going to equal negative 3. And if you try it out, 3 to the negative 3rd, that's going to work, right? 3 to the negative 3rd is 1 over 3 to the 3rd, which is 1 over 27. Okay? So all of these examples on this page you could solve with logs, but sometimes you don't need to. So I wanted to show you some techniques that you can use to avoid logs, because sometimes that's easier, okay? But sometimes logs are unavoidable. So let's start getting into logs. Okay, log stands for logarithm, right? So this is an equation, and I call this exponential form, okay? So it just means it's written with an exponent. It's not an exponential function, actually, because I don't have a variable in the exponent. But it's exponential form of an equation, okay? And this same equation written in log form is going to look like that, okay? So to write an equation in log form, first step, write the word log, okay? And then your base over here is this, right? Is the 2. And here's where the base goes. It's going to be a little subtext for the word log. So it's kind of a little written small and down low a little bit, okay? And then, so I have an x here, but I'm realizing that this was a typo. I wanted this to be an 8. 2 to the 3rd equals 8. I'll fix that on the note-taking guy. Okay, so my exponent is the 3. There's another bell, sorry. Okay, so when you put something in log form, the exponent is going to be isolated. And that is kind of the point of logs, that you can isolate an exponent. And that's especially useful if the exponent is a variable, which it isn't here, but you can still write any equation with an exponent in log form. Okay. All right, and then there's the contents of the log are just the number that's left over. Okay, so if you get the base and the exponent in the right place, this is what I call the contents of the log. And you might have multiple terms in there when these get more complicated, but to begin with, it's just going to be a number or a variable, okay? And that corresponds to that piece, okay? All right, so making this generic, hey, B here is going to be my base, okay? So this is the base. The isolated part in log form is the exponent. So the C should be the exponent, okay? And then the contents of the log are over here, the leftover piece. So this is, that same equation written in exponential form. It's really important that you're able to go back and forth between log form and exponential form. A great majority of the problems in this chapter, you're going to need to do that. Okay. All right. There's another important formula you need to know. It's pretty simple formula, but the change of base formula, sometimes you might want to change the base of a logarithm, and you can do it by rewriting a log equation as a fraction. Okay. And what you're going to do is put the log of A, I'm going to read this as the log of A. By the way, this would be log base 2 of 8 equals 3. That's how I'd say that out loud. This is log base B of A equals C. Okay? So I'm not going to put a little subtext here. There's no base in there, and I'll get back to that in a minute. Okay? And then on bottom, I'm going to have log of B. Okay? And you can actually change this to any base. So you could write it without a base like that, which is actually base 10, and we'll get into that soon. But I could also put whatever base I want in. So say I wanted it in base 7 for some reason. As long as I have the same base on top and bottom of the fraction, it's going to work like that. Okay? Now it's really important you remember which log goes on top and which one goes on bottom. So you see how the A is higher up than the B? So that's how you can remember that log of A should be in your numerator. And since the B is lower, log B is going to be in the denominator, right? I just chose random 7s, but I could have put 13s there or 999 or whatever I want, okay? So that's how change of base works. Okay, so let's look at this. We're going to find log of 10 on a calculator, okay? So any scientific calculator, you should be able to take logs. If you can find a log button, then you're in good shape. So there's my log button. It's about halfway down on the left side. Okay, so I'm going to click log and then just 10, and I'm going to hit enter. And this equals 1. Okay, so log of 10 equals 1. Okay, so let's think about what that means. If I've got no base here, right? I've got no base written, but I need something to the first power. So whatever goes here, this is invisible right now. Okay, it's not a 0, it's just a blank. So something to the first power, here, I'll make a little box here instead of, so it doesn't look like a 0. Something, if I translated something to the first power is going to equal 10. Well, that would have to be 10, right? So that means this is actually base 10, okay? So when if you've got no base written, it actually just means we're in base 10. Okay, and this is called our common log. It's kind of like with a square root, you don't write the 2 as the index because that's just the most common type of radical you can have. Same thing here, base 10 we use a lot, and so you don't need to write the 10 if it's base 10. Okay, you can write it, but you don't need to. You could write a little 10 in there. Okay, all right, and that is going to be key because your calculators are going to be programmed, all of them, to use base 10 logs. Okay, and there's ways to get around that, to change the base or to use the change of base formula, but we're going to be using common logs a lot, okay? So let's look at this example. So this is one that I would not be able to solve with those techniques because 3 to the second is 9, 3 to the third is 27. So it'll be a little more than 2. I could estimate it to be 2.1 or 2.2, something like that. And you know, I could play around in my calculator and get a decent guess, but I can't get an exact answer using the algebra techniques that we have at our disposal. But we can do this with logs, okay? So first step is to rewrite this in log form. So I write the word log. My base is 3, okay? The exponent is what gets isolated. And I want to leave a little space because the 10 is going to be the contents of the log, okay? Now, when I hit the log button on my calculator, some calculators, it might give you a place where you can type in the base, but mine doesn't do that, okay? So that means I'm stuck with base 10, okay? And that's where the change of base formula is going to come in. So I'm going to rewrite this. X is going to equal then log of 10 over log of 3. And so now this is in base 10, and I can type it in my calculator, okay? So let's see, log of 10, we already did this one, that's 1, right? I'm going to put approximately equal because the bottom, when I type this in, log of 3 is 0.477 roughly, okay? So what I'm going to do 1 divided by that decimal, okay? So it might be better actually just to type this all into your calculator. So because we don't want to round our answers as we go. So I'm going to type this in as of log of 10. And you notice before I wasn't closing the parentheses because I wasn't doing anything else afterwards. But here I do want to close the parentheses and write this as log 10 over log of 3. It doesn't really matter if you close this N1 because nothing else is happening there. And then I've got 2.095 roughly. Okay, so I'm going to round that to 2.10. I'm going to the nearest tenth here, but you could round it to whatever place. But don't round your answer until you get to the final one, right? I did it there just so I could write down the approximation of log of 3. Okay. All right, so let's try this next one. So I'm going to rewrite this in log form first. Log base 7 of 100 is going to equal x. That's how it will look. Okay, and then I want to put this into my calculator. So some calculators, again, you might be able to just type in the base. Mine, I can't do that. I got to write it in like so. Log of 100, 10 to the something is going to equal 100. Well, that should be 2, right? 10 to the second. So the top of this, log 100, is going to be 2. But I don't know what log 10 raised to some power equals 7. I don't know what that is. It's going to be a decimal. So I'm just going to do this on my calculator. Log of 100. Close the parentheses, divided by log of 7, and then I've got 2.37 roughly. Okay, so once you get the hang of this, the big part's rewriting the equation in log form, and once you get the hang of it, these go pretty quickly. Okay, so log, my base is 5, the 496 is going to be the contents of the log, and the x gets isolated. And then typing that in my calculator, and you'll probably get to the point where you won't write this step down to change the base, and that's okay. You'll just know that's going to be log 496 over log 5, okay? And so that's how I'm typing this in. Don't forget to close the parentheses because otherwise it'll take the log of 496 over log of 5, or at least it might do that depending on your calculator. So type it in like that, 3.86 roughly. Okay, one more time here. My base is 8. 6, 7, 8, 9 is the contents. X gets isolated, and I'm going to type that in my calculator in base 10 form as common logs. So there's my change of base. And then I've got 4.24. Okay. Okay, let's look at graphing log functions, exponential and log functions. Okay, so this is our parent graph for exponential functions. It's this, if I did 1 to the x, 1 raised to any power equals 1, so it'd just be a flat line. So that's why we're using 2 as the smallest integer we can use, okay? So we can make an xy table here. Let's see. If I put in 0 for x, 2 to the 0th equals 1. If I put in 1 for x, 2 to the 1st equals 2. And that's all I put room for on here. So let's go into the negatives. If I put 2 to the negative 1st, so let's see. If y equals 2 to the negative 1st, then y is going to equal 1 over 2 to the 1st, or 1/2. So 1/2, okay? And if I put in a negative 2, then I've got 1 over 2 squared, which is 1/4. Okay, so let's graph this. We did this in another section already. Got 0, 1, 1, 2, and I didn't put it. Let's put in 2 as well. That would be 4, right? So 2, 4 is on this graph as well. Okay, then I've got negative 1, 1/2, and negative 2, 1/4, something like that. Okay, so I'm going to get a growth curve. This is going to have a horizontal asymptote at the x-axis. Okay, so I'm just putting HA for horizontal asymptote. Okay, so if you needed the equation of that, that's the line y equals 0. Okay, or you can just say it's the x-axis. Okay, so that's what happens when we have a base that's more than 1. We're going to get a growth curve. If we have a base less than 1, then this is actually going to be decay. Okay, this one's a growth curve, and this one is going to decay. And that is because of the base. When my base is less than 1, I'm going to get a decay curve. Okay, and we can make an xy table just in the interest of time. 1/2 to the 0th is going to equal 1. 1/2 to the 1st equals 1/2. When I plug in 2 for x, 1/2 to the 2nd, that's 1/2 times 1/2 would be 1/4. Okay, so it's going to look like that. If I put in a -1, then I've got 1/2. That's 1 over 1/2 to the 1st. 1 divided by 1/2 is the same as 1 times 2 over 1, and that equals 2. Okay, and I can do the same kind of calculation. If I plug in a -2 here, I'm going to end up with 4. Okay, and so this is still going to have an asymptote at the x-axis, a horizontal asymptote here at the x-axis at y equals 0, but it's just going to be a downhill line. Okay. All right, so anytime you get a base more than 1, it's growth. If you have a base less than 1, it's going to be decay. Okay. Now, the horizontal asymptotes we've seen so far are at the x-axis, but they can move around. They could be higher or lower than that. Okay. Now, I could rewrite this equation up here like so, right? Or I could write this one like so, just by adding 0. And there's no point in doing that, but this is going to correspond to the horizontal asymptote. Okay, in both of these. So if I'm adding something other than 0, then that horizontal asymptote is going to move up or down. Okay, so let's look at this next example down here. I do have something added here. So my horizontal asymptote, instead of being y equals 0, it's going to be y equals 3. Okay, so I'm going to plot that first. Y equals 3, so it's going to raise my horizontal asymptote up to here. Okay, so let's do this next one. So this is my horizontal asymptote here. I'm going to go back and finish this, but my horizontal asymptote is going to be y equals -5. So there we go. I usually graph the horizontal asymptote first because it gives you a guide where, like it did on these first two problems, that your curve is going to approach these horizontal asymptotes. Okay, they're kind of like guidelines for drawing these. Okay, so let's get back to this one. Okay, now you can do an XY table again, but this is going to be the same as this, except everything is moved up 3 units. So I'm just going to follow the shape of this graph, except instead of starting from the x-axis, I'm going to start from my horizontal asymptote. Okay, so that first point was 1 unit above the asymptote, so same thing's going to happen here. And then, you know, I went up 1 to the right 1 from there, right, to get to the next point. And let's see, I went up 2 to the right 1. Okay, and then I've got, if I go left 1, I'm up a half unit, something like that. So I'm using this same shape, exact same shape, just with this new horizontal asymptote. The whole thing is shifted up 3 units from the example above. Okay. Now, this next one, I know this is going to be a growth curve again because my base is 2. My base is still 2. My base is not 6 because it's 3 to the first times 2 to the x. I'm only interested in the base of the variable exponent in terms of growth or decay. So I know this is going to curve upwards somehow. Okay. So the thing is, the 3 is going to change how steep it is. Okay. So I can't really make a guess based on either of these other, like this parent graph up here. Okay. So what I usually start with is finding the intercepts. Okay. Let's find the x-intercept. Here, I'll do this so it's clear. Okay. So my x-intercept, what I'm going to do is plug in 0 for y into the equation. Okay, and I'm going to try to solve this for x. Okay, so I'll start by adding 5 to both sides. Don't simplify this to 6x. This is not, or 6 to the x. This is not 6 to the x because it's 3 to the first times 2 to the x. But what I can do to get rid of the 3 is just divide both sides by 3. I'm trying to isolate the x here, right? So that gives me 5/3 equals 2 to the x. Don't simplify that to, don't write this as a decimal approximation. We want it exact. If it was 5/4, sure, you could write it as a decimal because it'd just be 1.25. But this is we want this exact, okay? And now I'm kind of stuck. Taking the square root of both sides isn't going to do anything. But wait a second. I've got logs on my side, and that can help you isolate a variable exponent, okay? So my base is going to be 2, right? The x is going to get isolated, and then the contents of the log are going to be the 5/3. So I'm just going to put that in parentheses so it doesn't look like the base is 23 or something, right? So it's clear what the contents are. And that's something I can put in my calculator, okay? I'm going to put this in as log of 5/3 over log of 2. Where am I? Log of 5/3. Divide that by log of 2. And I'm going to get 0.7, I'll call that 0.74. Okay, so there's my x-intercept. So now I know that that's where it's going to cross the x-axis at 0.74. I can't graph that, super accurately, but I can eyeball it. 0.74 would be something like that, right? I'm going to do the same kind of thing with the y-intercept. So the y-intercept is actually easier just because I won't have to use logs to solve this. So going back to the original equation, plugging in 0 for x, and then, hey, I know 2 to the 0th equals 1, right? This equals 1. So I've got 3 times 1 minus 5. Hey, 3 minus 5 is negative 2. Okay, so that means my y-intercept is there. Okay, and now I can graph this. This isn't going to be the best graph in the world, but I know it's going uphill, and I know it's going to approach this line, and I'm just going to make a growth curve that fits with that asymptote and those 2 points that I found. Okay, it could be like on this problem, there is no x-intercept, right? So if I was trying to graph this with this, I could find the y-intercept in the same way. The x-intercept, it's just going to be undefined if you try to find it. But what you could do is just plug in something else for x. I could plug in 1 for x, for example. So then 2 to the first plus 3. If I plugged in 1 for x, the y that I get out would be 5, and then I've got another point. Okay, so they don't have to be the intercepts, but they're nice to use because then you'll always have the x and y axes on the graph, and then a lot of times it'll make it nice and easy to sketch in after that. Okay, let's try some more on the next page. So, when you add or subtract to the end, it's going to move the whole thing up or down. But there is a way to move the function left or right. That's going to happen when you're adding and subtracting to the x inside the variable. Okay. So, what this is going to do is it's going to move things to the right, okay? So our this is going to be our horizontal asymptote. It's going to be at y equals 0, okay? But what I do to find out going left and right, if you take the exponent and set it equal to 0, then x would equal 1, and this means I'm going to go 1 to the right. Okay? So I'm going to have a growth curve still. I know this is growth. So it should be kind of going uphill from left to right. Okay? And it's also going to get shifted to the right, which actually doesn't help that much with graphing this. So I'm still going to just find the intercepts. Okay? So here's my horizontal asymptote. Okay, let's find the y-intercept. So plugging in 0 for x. So that's going to be 1/2, right? So my y-intercept is 1/2. Okay. For the x-intercept, this is actually not going to cross the x-axis. I can see that because the horizontal asymptote is right on there. But let's just explore this a little bit. If you plug in 0 for y, I can put this in log form. So log base 2 of 0 is going to equal x minus 1. Okay. So I can put the left side of this in my calculator, and if I get a number out, I'll just add 1 to that to get x. But let's see what happens here. So this would be log of 0 over log of 2. Oops, forgot to divide over log of 2. And I get this error because this doesn't exist, okay? This is undefined. So x doesn't equal anything. And the reason why is because if you think about this, look at the left side of this equation. 2 raised to some power equals 0. You can't do that because even 2 to the 0th equals 1. And if you do 2 to the negative 1, then it comes out to 1/2 and so forth. It's anytime you have 0 as the contents of a log, it's going to end up undefined. And it makes sense because there is no x-intercept here, okay? So you could kind of just sketch in a growth curve from there. If you wanted another point, you could do something like plug 1 in for x. So let's go ahead and do that. If I plug 1 in for x, then I got 2 to the 0th, and that is 1. So hey, there's a second point, and that's enough to kind of get a sense of how this curve is going to go. I know it's going to approach the asymptote but never quite get to it, so it'll look something like that. Okay. All right. So this would end up moving things left 3, but that again is going to be kind of hard to see on the graph, right? Because moving this left or right, it's still just going to cross the y-axis somewhere. Okay. So here is my horizontal asymptote. Going to start with that. Okay, I know this is going to be a growth curve. Oops, I'm off screen. I know this is going to be a growth curve again because the base is more than 1. Okay, let's find the y-intercept. Plug in 0 for x. 2 to the 3rd is 8. Don't need a calculator for this. So my y-intercept is 4. Okay, and let's find the x-intercept. So this one, I believe, is going to cross the x-axis somewhere, right? That one didn't, but this one is going to cross the x-axis. So let's plug in a 0 for y. Okay, I'm trying to isolate x, so first thing I'm going to do is add 4 to both sides. And then I'm going to be stuck. Taking the square root doesn't do anything, then both sides will just be in a radical. Okay, and I can't take the x plus 3rd root because I don't know what x is. But what I can do, I got 2 options. I could write both sides in base 2 actually, or you could write this as a log, okay? Just for fun. And so in log form, it would be log base 2 of 4 is going to equal x plus 3. But let's use this other technique because I don't even have to mess with logs then. 2 is going to equal x plus 3. I rewrote 4 as 2 to the 2nd, right? And then I just subtract 3. So x is going to equal -1. So that's my x-intercept. There we go. And I still know it's going to approach that asymptote, so I'll just kind of make it fit from there. And you could get more points if you wanted to get more accurate, but it's going to look something like that. Okay? All right. A lot in this section. I'm probably going to have to break this up a little bit. But next up, we're going to find this is called the inverse. When I have f to the -1st of x, this is going to be the inverse of f of x. Okay? So this is just function notation of an inverse. Okay? And what an inverse, the way you're going to find an inverse is by switching the x and y. And once you've done that, solve for y. Okay, now this equation doesn't have a y in it, but the f of x kind of acts like a y. So let's just pretend that's y for now. Okay, I'm going to just switch the place of the x and the y. All right, and then I need to solve this for y. I need to get y isolated. And I'm going to need a log for this, right? So I'm going to go log, my base is 2. The exponent gets isolated, and I'll leave some space so the x has to go in that slot, okay? So now I've written this. Now the only thing left to do is put it back in function notation. Since the problem started in function notation, I probably want to answer in function notation. So I'm going to rewrite the y as f to the negative first of x, okay? And I'm going to flip this around too, but that doesn't really matter if you do that. But here is the inverse then of this exponential function. So if you have an exponential function and you find the inverse, it's always going to be a log, and vice versa. The inverse of a log is always going to be an exponential function, okay? Let's graph both of these. Hey, we've graphed this one before, okay? So we graphed this earlier, so I'm going to go through this kind of quickly. There's nothing added to the end for this first one. So there's my horizontal asymptote at the x-axis, okay? It's going to go through that point, and let's see, if I did 2 to the first is 2, so it's going to look something like this. I'm just doing a quick graph here. This one is f of x. That's y equals 2 to the x, okay? I'll use a pencil to do the other one, okay? When you graph the inverse of something, you're just going to switch the x and y's, okay? So, for example, 0, 1 was on f of x, so that means 1, 0 is going to be on its inverse, okay? And let's see, I've got this other point here. This was the point 1, 2. 1, 2 was on the original function. That means 2, 1 is going to be on the inverse. So if you just switch the x-y pairs, okay? So this is actually going to get reflected over the line y equals x. You might remember that from geometry, okay? So it's going to be kind of a mirror image over this line. So actually, before I get to drawing the curve, since this had a horizontal asymptote right here, if I think about switching the x and y's there, that means the inverse is going to have an asymptote. Whoops, broke my pencil there. Inverse is going to have an asymptote on the y-axis instead. So this isn't a horizontal axis, it's a vertical axis. Or vertical asymptote, I mean. And the equation of this is x equals 0. But it's just the y-axis, okay? So that gives me a curve for drawing, a guide for drawing this curve, okay? And this one is the inverse. So you can kind of just switch the x-y pairs. You can also always just think of it as reflected over the line y equals x. So here's the line y equals x. It's a reflection over that, okay? But one of the morals of the story here is that log functions are going to have vertical asymptotes, where exponential ones are going to have horizontal asymptotes. Okay. Okay, and on to the last page here. So yeah, we're going to use this to graph some log functions, this idea. Okay, so log functions always will have vertical asymptotes. So here, in exponential functions, I'm going to just put this in the corner here, are going to have horizontal asymptotes. And a log function will have a vertical asymptote. Worth remembering that, just memorizing it. Okay. All right. So these are log functions. These should have vertical asymptotes. Here is kind of our parent graph for a base that's more than 1. Here's our parent graph for a log with a base of less than 1. Okay. So let's plot these. Okay. So I know this one doesn't have anything anything added. So if it doesn't have anything added or subtracted anywhere, then your asymptote is just going to be the y-axis, okay? And I'll get to how sometimes those will move around, but we'll get to that on a different example, okay? So there's my asymptote, my basic asymptote, all right? And then let's see what happens when we plug in 1 for x. When I plug in 0 for x, I'm going to have the contents be 0. It's going to be undefined because it'll be on that asymptote, okay? But if I plug in 1 for x, then, hey, 2 to the something equals 1. That would be 0. Okay, you could put that in your calculator as you know, log 1 over log of 2. But when I plug in 1 for x, I get out 0 for y. So 1, 0 is on this, okay? And then if I plug in 2 to some power equals 2, that would be 1. Right? And you can plug that into your calculator. Log 2 over log 2 would be 1. So 2, 1 is on the graph, okay? And if you plug in negative 1/2, or it's positive 1/2 rather, you'll get negative 1 out for y. So this is going to end up looking like this, okay? You can kind of think of it as growth because it's still kind of going uphill from left to right, okay? And this one's going to be reversed around. I'm not going to write the x, y pairs. It's still going to go through this point, but it's going to be flipped around from this one, okay? So it's going to do this instead when your base is less than 1. So I still kind of think of when your base is more than 1, I think of it as growth, and this one as decay when your base is less than 1. Okay, so it just determines whether it's going uphill or downhill. Okay, all right, so let's move on to a more complicated example. All right, so remember when we had this kind of stuff, that if you set this equal to 0, when we did this with exponential functions, that was determining moving left or right, and it's still going to do that. So this is going to move left 1 unit. Okay. Now, it didn't really matter that much with exponential functions because when you move a horizontal asymptote left or right, it's going to stay in the same place. But, hey, if you have a vertical asymptote and it moves left or right, that is going to make a big difference. Okay. So the movement left or right, which comes from the contents of the parentheses, the contents of the log, that is going to determine the horizontal asymptote. So my horizontal asymptote is going to be x equals negative 1, okay? So let's plot that. Sorry, I'm off screen with that part, but I'm going to put that in my picture. Hey, so there's my horizontal asymptote. Really helpful to have that in place. Get my zoom worked out here, okay? And then, hey, I can see this is growth, so this should go uphill from left to right. It might look something like this, right? It's going to curve something like that. But let's get a couple of points placed so that we can get a better graph. This is going to move everything down 3, but you know, with my horizontal asymptote moving up or down 3, it doesn't really do much. It is going to affect where the points I find are, but we don't really need to worry about that. We'll just do the math, and that will take care of itself. Okay? So let's find the intercepts. I'm going to find the x-intercept. I'm going to plug in 0 for y. Okay? Don't simplify this to x minus 2. You can't do that because the quantity x plus 1 is inside of the log, and the negative 3 is just subtracted afterwards. Okay? So that makes a difference. Don't simplify that, the 1 and the negative 3, because yeah, this is the contents, that is not. Okay? So I'm trying to isolate x. I'm going to start by adding 3 to both sides. Okay? Now I'm kind of stuck with my old school algebra methods, I'm going to have to put this in exponential form. It's already in log form, so let's put it in exponential form. This is my base. Okay, this is going to be the exponent, the isolated part. The contents of the log go in the last remaining slot. Okay, and hey, I can solve this, right? 2 to the third is 8. Subtract 1 from both sides, and x equals 7. So my x-intercept is 7. So let's see, 1, 2, 3, 4, 5, 6, 7. There it is. Okay, and let's find the y-intercept. I'm going to plug in 0 for x into the original equation. Okay, and the parentheses are really important. Again, don't simplify that to log base 2 of negative 2. It's not the same thing. What I want to do is simplify this in my calculator. When I get the answer, I'll subtract 3 from it. Okay, so I'm going to put this in my calculator. I'm actually not going to put this in my calculator because I can do it in my head. But if you were to put it in your calculator to look like this, then you'd subtract 3. Okay, now I'm just looking at that thinking, oh, 2 raised to some power equals 1. Well, that would have to be 0, right? But if you're not following me there, go ahead and put your calculator, that's fine. And then y equals negative 3. So there's my y-intercept, and now I can make a pretty good sketch of this. Whoops, that was a pretty bad curve. But that's okay, it's just a basic sketch. But there it is, okay? And that's it for this time. See you next time.